folks. Welcome to the second half of the workshop. Strong work. Strong work. Thank you, Anna. No, they're doing, that's pretty good, actually. That was pretty good quieting down. The teacher didn't have to yell. Okay, are we recording? Okay. Welcome, everyone. Sorry, my notes just went away. So we have this panel is called State of the Science to Support Long-Range Planning. And the purpose is to explore the relevance and applicability of what we heard this morning to current work in the Delta region. And the participants are encouraged to reflect, are encouraged to reflect on how the cutting edge climate science that we learned about and modeling approaches can be integrated into long-range planning. And we've got a great panel. They're here. I'm going to start introducing them. I was asked to do one quick housekeeping thing. For those of you who want to refill your water bottles, the kitchen does have a spigot where you can refill water bottles. So without further ado, I don't want to waste our time because we're a little behind already. I'm going to start with Dan Cayan from UC San Diego, who's going to start us off on the panel, and we'll go from there.
Thanks, Lisa. I'm going to focus on drought because it's such a cruel and seemingly ever recurrent impact. This is work that I've been doing with Lou Su, who's a postdoc that's a UCLA Dennis Lettenmeyer product, and now she's wandered into our spider web. Let's see, a lot of this is the earlier talk kind of introduced much of this. This is another lens at how California is special. And in this case, we're looking at the propensity of regions in the United States to have dry events that dip below 3/4 of their annual long-term average. And you can see how California stands out. It kind of mimics the coefficient of variation that Mike produced. And here's another record. This is the essentially the Delta watershed precipitation annually for water years going back to the early 1900s, and you don't even have to smooth it. Just color dry and wet, and it's really impressive to see these runs. And the other thing that impresses me is that I think there's a bit of a propensity for dry spells to be a bit more persistent than wet spells, although maybe that's arguable. Variability, not only historically, but as we move into the future, is impressive. And there's this, we made the point earlier that especially the wet years in the future become a bit more prominent. You can see that towards the end of the century there in the left-hand panel. This is from an ensemble of downscaled CMIP-6 simulations under the 370 scenario. So here we have left-hand side of each of these panels is the historical period, and the right-hand side is future. And in this case, we extracted model runs that fell in close to the median amount of precipitation. So you can see the precip there, upper left, they're both about the same. But of course, the temperature rises hugely in the future compared to historical. That's the lower left, and evaporation through the eyes of VIC, the variable infiltration capacity model, increases greatly. And interestingly, as it has to, because you're removing more water from the system, the runoff actually declines. So we're removing usable water from the system. And when you look at how this plays out over the rim basins of the Delta watershed, and you look at the lowest precipitation decile, precipitation is low just about everywhere. Well, these are higher basins, the higher Sierra, and these other ones are lower. But I'm out of control. Sorry. In any case, when you come to runoff, what you're impressed with is how the middle and high elevations really become quite acute and not the low ones. So the other thing that's really impressive when you look at runoff during essentially all of the years with low runoff is over time how the runoff season migrates away from its traditional later spring period to the more core winter months. And so we mentioned that precipitation is becoming sharper seasonally, but runoff is really becoming sharper, and particularly in these dry years. So it's, that's, I think ecologically and probably from human perspective, that's really important. Now, we heard this morning that that GCMs were depauperate in representing some of the long period variation. So what we did here is we have a census of different dry spells between 1 and 20 years. This is all historical period. OBS are the right-hand pair of each bar, and it's the most, in that case, it's the most extreme drought that we've seen since 1895 in the observed record. And then what I've done is I've taken all of the 13 CMIP6 simulations that we had in this case, and I've arrayed them to look at the driest event in 30 historical years, something like that. And so I'm stacking up the CMIP against the OBS here. The whiskers are show the entire distribution from the 13. So I'd argue that CMIP is actually doing a pretty faithful job in replicating droughts of all time scales in the historical CMIP record. No surprise, there's a huge shift in, not in precipitation so much, that's the downward hairs here in this plot. Upper is historical and lower is historical and upper is future. But the runoff shift is really profound, and it's really profound for the dark part of this is the so-called driest years, and there's a lot of shift in those years. So I'm going to get off the stage because Lisa was such a cruel taskmaster. Let's save that for the discussion, and I think.
Okay, next up, we have Mike Dettinger of UC San Diego as well. Some collusion here, I think.
Hi, so this is going to be completely different. Yeah, Ovi said, just introduce yourself, and maybe he had seen me talk to Peter's SWP CVP committee a year ago now, pretty much the same time of year. And maybe we could use some of that stuff. And I had picked up by looking at various versions of the agenda that uncertainty was kind of a big deal today. And so I just want to talk to you about a couple of things real quick. By the way, I'm Mike Dettinger. First off, my answer to the question of what have we learned in the last, I'm going to say, dozen years, I think these are the two big things that, from my perspective, we've kind of gotten our hands around. One of them is that I'm telling you, I looked back, in the record and all that stuff, and, back in 2013-ish, 2014, that period, we were still sort of getting the deer in the headlights look whenever somebody from the ISB or anyone from DWR or somebody said, is it going to get wetter or drier? That's a simple question. Is it going to get wetter or drier? And that top diagram there on the left is some work in 2019 that we did. Sasha Gershinoff led it, but where just took some various ensembles of projections and looked at the total California precipitation and what you're supposed to get, those whiskers and all that stuff. But fundamentally, you get more or less zero. I mean, if it's not zero, then it's within the error bars, I'm telling you. We were always stuck with this situation where half the models would get wetter and half the models get drier, plus or minus one or two models. And that just made everyone crazy when we would say that. What are we supposed to do with that? But starting around 2013 or so, folks started digging in and looking at what was going on to give you that. And the bottom two here on the left tell that story, or at least this is my version of the easiest way to show it. And that is that on the middle there is the precipitation that comes from the atmospheric rivers in the projections. And what you get is that on the whole, in a typical ensemble, and I can tell you in my own work, 8 out of 10 of the models would go this way. So that kind of level of consensus, you would get a significant increase in the amount of precipitation out of atmospheric rivers. But if you looked at all the other storms that showed up in town, you get the bottom one there, which is, as it happens for these ensembles, and there's about 4 different ways of cutting the cake to get various different ensembles here on each of these, but it's roughly the same amount less that you get from other storms. And I've done this with, forget about atmospheric rivers, big storms, 95th percentile and above, or versus everything else storms. And this is kind of the story you get. And so it was roughly a dozen years ago that Dave Pierce and Dan and others, we started to figure that one out, that actually, that we still can't, I would argue that we still can't tell you, one way or the other how it's going to work in terms of that top diagram. But what we know is the thing that will be on the next slide is, there is what I think is as clear a story as you're going to get as to what precipitation is going to do in California under climate change. And on the far side, on the right side, is the other part of the story, is that we all knew forever that as temperatures go up, surely the atmospheric demand will go up. Sure, but honest to God, for people like me who aren't in Mike's group, it was only roughly about 10 years ago that I started seeing the ETO data starting to trickle out into the real world where we were seeing it. And what you see there is that you see what we kind of expected, which is that the demand will increase as it warms. But what from my perspective, it's that we could finally start to really put numbers to it and, you know, and say more than it gets warmer, things get drier, you know. These guys really gave us the tools, the historical data tools to really start making sense of, or turn them into projections. So that's my two big breakthroughs as far as I'm concerned. So anyway, first thing, one thing I have to say, and we've heard this, several people said it a different way, but that's my way of saying it, is California will increasingly need to manage its floods to get through its droughts and its droughts to get through its floods. Because, you know, and currently our systems are set up where more or less we're always trying to drive things towards the middle, towards normal with our reservoirs and irrigation plans and all that stuff. And when it deviates drier or wetter, we're doing what we can to kind of, we'll nudge it back towards where we need to be. But what I see in that first diagram is, you know, that we're going to be losing the normal stuff. And, you know, increasingly that's a horrible way to say it, but increasingly the normal years, the normal seasons, I have to say this is kind of not necessarily on an annual scale, some vague time scale here, but we're going to have more periods that when you take both demand and precipitation into account are giving us droughts, whether they be years or seasons or whatever, you know, multiple year periods, whatever, and punctuated, interrupted by the occasional really big storm or really big wet year, okay? And that's a whole different world. And especially because you can't have both of those things and the middle sort of unchanged. So that what you end up with is this situation where we need to take the water from the floods, and we just can't treat that as waste product or a hazard. We have to somehow use that water. And during the drought years, you know, one other thing that goes on is we're creating space where maybe that'll allow us to catch some of those floods when they finally come back around. This is the whole kind of flood-mar notion. So this is really important, I think, from what I heard this morning and from what I've been worrying about for quite a while. And pushing right along, and what does that look like on the ground? Well, God, you know, you make your slides and you go into a meeting and people stomp all over them. I don't know what the heck. But you know, here's my slide for two ways that we are actually getting down to business of how do we manage water resources in California that are more based on, that rely more on the extremes, which is what we're going to have to do in the future. One of them is FIRO, Forecast Informed Reservoir Operations, and the other is FloodMar. I do want to say, based on the question and answer over here, both of these things have got huge, they began with huge amounts of local agency and local, I won't say public, that takes a while, but local agencies and the like, and practitioner agencies input. On the steering committees for the FIRO, there's always generally about twice as many practitioners on the steering committee as there are scientists, if not more. And on the FloodMar, that's largely a DWR process that when I see it, I'm not involved in that, but I get briefed on it once in a while when I manage to be at the right place at the right time. And they're working very closely with Merced County and the irrigation districts and all that to try and figure out how you do that so that people will buy into it and will not be screwed in the process. I do want to say down at the bottom, those are both water resources. I have no idea how to do this for ecosystems in the Delta, but I believe that's question number one for you guys on ISB. You really got to get down to that because you're going to have the equivalent for the Delta. Just going to have to. Okay, now I must be out of time almost, but here's my other. So we wanted to talk about uncertainty. Here's something that you might want to view as an uncertainty, but this one isn't necessarily a bad uncertainty. Okay, how can it not be a bad one? And that is up the top, hydrologic impacts of all these various changes, storms, drought, demand. Virtually everything we heard about this morning are not as written in stone as you might expect. Once that, well, with the exception of the stuff up in the atmosphere, precipitation before it hits ground, and temperatures and the like, those leave out of this discussion. But once it hits the ground, if we're talking about wildfires, if we're talking about runoff, if we're talking about floods, if we're talking about hydrologic droughts, they're not necessarily written in stone. There is this divide that I'm trying to illustrate by this cartoon. Up in the upper box are the climate modelers and the hydrologic modelers. And I can tell you, as somebody who lives in the hydrologic modeling side and has been down the hall for 40 years from the climate modelers of various stripes, that we don't know anything about what the plans are for forests in the watersheds or management of reservoirs up in the watersheds or whatever, modifications to the stream networks, all that stuff. So what do we do? What is any modeler going to do under these circumstances? We're going to say, all other things being held equal or the same as historical, what happens if the climate changes, precipitant temperatures change the way they would if the greenhouse gases continue to rise? I mean, perfectly rational. I'm not picking on them. That's what you do. When you get down towards the practitioners, the reservoir managers, and this is a water resources oriented one, and just general supply and demand issues on the ground, they're not atmospheric modelers, and most of them aren't hydrologic modelers. And so what are they going to do? They have to pretty much accept what top box gives you. And so I'm here to tell you that virtually every climate projection of stream flow and floods and that stuff that you heard about today, or that you see being used by almost anybody in the Delta or in this part of California, make that assumption up at the top. And it's so basic that we rarely mention it. Nobody mentioned it today. I was keeping track, and it's not, it's just the truth. But the fact of the matter is that that dictates, that ends up dictating 5% less runoff and floods will be 50% bigger or whatever the number is. And we tend to take those as though they're written in stone. There are things we can do to push back on those, okay? So what do I mean by that? Here's my point is that if you start doing things, there are things to do in the headwaters and the watersheds and the like that could push back on that, could reduce the size of the floods. Not fix them, I don't think we're ever going to get to that, but reduce the impacts. Keep the flow in the river going a bit longer in the year. There's any number of those things. And there's nothing, it's not breaking the rules if we start to think about what do we do, not just to adapt to the changes that you've heard about all day, but to reduce how those impacts as they come flowing out of the range. And frankly, I would, there's a handoff between expertises, is the divide between those two boxes. But you could also almost, I will claim, since I'm out of the game, but I will claim that you could put another label as a dividing line, and that's pretty much the range front, the major reservoirs at the range fronts. Shasta, Oroville, Folsom, down the range. All of our adaptation efforts tend to be focused on so much water will come in the future, and now how are we going to manage that down the system to the Delta and down to Southern California and all that stuff. But there are things we can do up above those major reservoirs that could make a difference. And I'm sure I'm over time now. I'll just say in December of 2023 in SVUs, some friends and me wrote an essay in there where we discussed we talked about that, and then we talked about basically about three kind of low-hanging fruit. The low-hanging fruit mostly because these are already being funded and done. They're just not being funded and done to fix the climate change impacts, or enough in some cases to fix the climate change impacts. But they're already being done, so it's not like there's nothing we can do about that. You know, it's not too big a problem so that we can't do anything. And frankly, I'm hugely convinced that there's a lot more options out there that aren't quite so low-hanging. And my bottom line in all of this stuff, so read that article, it's not very long, but I'll just say that my most radical statement of all is I believe that the Delta Stewardship Council / Delta Science Program really ought to be at the table when they're talking about things that are going on up in the headwaters. It's really not outside your mandate, and it's the sole focus on right in the Delta is leaving things on the table that, other options on the table. Okay, I mean the flagship journal for this stuff is San Francisco Estuary and Watershed Science. I think sometimes we've forgotten that.
Thank you, Mike. Yeah, I figured. Thanks for that little bit of optimism. We're short on that today, so thanks for that. So next we have Stefan Telke of Cal Poly. As soon as Edmund gets his slides up.
Okay, perfect. Thanks for all being here. This is a picture of the Delta, probably 20 miles away from here at Tyler Island. For those of you who haven't been in the Delta, I would definitely recommend going there. You can see what the problem is and why this is such a big problem in this picture. The water level is high. The land below is much, much lower. That's a huge problem. It's a loaded gun in California. If the levees were to break, then it would impair water to 26 million people, all the farming. It's a huge linchpin of the whole water system in California. When I teach students, most of them don't know that. So my focus today is to look at historical records and try to see what can we learn from them. What can we learn also in terms of mitigation that we heard about in the last lecture. So to do this, the first thing you need to do is have some data, and I won't go into it too much, but we have recovered about 2,000 years of historical water level data in the Delta, going back in some cases to 1849, and we're in the process of analyzing them. If you take a look at the last 150 years, you can see what's possible. This is the left-hand graph is Sacramento. You can see in the 1900, water levels were actually higher than they are today. That's because of debris from hydraulic mining. In the next 20, 30 years, that slug of sediment went away, but there was also a lot of channelization, dredging, making the channels more hydraulically efficient, and that lowered water levels by several meters. Several meters. When we're talking about sea level rise, we're talking about a few millimeters a year. And then it has slowly been creeping upwards, and we see that in other locations as well. And that could be reservoir management, it could be subsidence. It's a big question. We can also see, using the San Francisco tide gauge, that river flow to the San Francisco Bay and to the ocean has greatly decreased over time, and the timing has decreased as well. So about a 25% decrease in the total amount. And if you take a look at the right-hand side of that graph, those are big flood events that happened in the 19th century. You can see the 1862 event there, about 25% larger than anything that came after it on a monthly basis. But you can also see some spring freshet type of events that don't happen anymore. All right. If we take a look at the San Joaquin River, if we just take a look at the water levels at the Mossdale crossing, if you had been on the Transcontinental Railroad in the year 1900, in the springtime, in June, you might have seen a water level of 5 or 6 meters. If you went in the fall, it would be down to 1 meter. So there's a huge seasonal variation in water level that doesn't happen anymore. If you move to the right, you see this degradation in the seasonal fluctuation of water levels to where it almost virtually doesn't happen anymore on average. The shading is sort of like the 25th and 75th percentile, so we occasionally have 19th century-like conditions, but mostly not. So that's just taking a look at some of the long-term water level trends. What do we know about sea level rise? And if you take a look at the coast, it's actually interesting. We see anywhere from about 2 to 5 millimeters per year, and that's being driven both by the global sea level rise, but also vertical land motion. Tectonics play a role. There's also some glacial isostatic adjustment. So 2 to 5 millimeters actually can mean a difference of a foot per century. But if we take a look at the delta, we just showed that river flow is important, so trends in river flow would be important. We know that we're extracting water. Does that lower water levels? There's also an attenuation of coastal sea level rise that has to happen. We know that if you go all the way up to Red Bluff, there's no sea level rise. But what is it in Sacramento? What is it in Rio Vista? What is it in Antioch? And then there's also the local subsidence, which I'll show you in a minute. So any of these factors can actually influence your water levels and therefore your flood risk going into the future. And it also is a opportunity, right? So like these can also be knobs that you turn to change your water level. So we wrote a paper a few years back showing what is the sea level rise over the last 20 years in the Delta. And if you just look at the colors, you'll see that there's a lot of variability. It also is somewhere between 2 to 13 millimeters a year. That's huge. That's like a meter a century difference in what the sea level rise will be. And it's being driven by locally variable vertical land motion. So there's some places in the Delta where there's probably groundwater pumping going on. There's other places where there's natural gas extraction. Those type of things cause compression in the ground and show up as a sea level rise, a relative water level rise signal. And it's a lot bigger than in San Francisco. So you can just quantify that. Anything that's blue on this map, dark blue, is a hot spot of vertical land motion. You see it's very spatially heterogeneous. That means if we had more gauges, we would probably see more heterogeneity. When you take a look at LiDAR measurements of the levees, they show in some places up to 50 millimeters a year variation, subsidence. Do you believe that? It's just based off of 2 LiDAR surveys, but this is consistent with that. So there's really big problems that have to be dealt with that have nothing to do with climate change. There's also this attenuation of the low frequency signal. You can't see this very well, but basically about 65 to 80% of, let's say, monthly variability at the ocean propagates into the Delta. So if there's a 20 centimeter El Nino at the coast, you might see 15 centimeters of that in the Delta. So not 1-to-1, but also not 0-to-1. In the top right corner of that graph, that's when you go up the Sacramento River, and so you get progressive attenuation, and so you get more attenuation. So, you know, at Sacramento, maybe it's 20 or 30 centimeters of sea level rise for each meter at the coast. And that's a hydrodynamic effect, and it depends on river flow to an extent that we don't really know yet exactly what that is. We can model it, but do we believe the models? It's an active research area. So what are some of the other factors? We know that high river flow matters a lot, especially in the eastern delta and in the Sacramento River. We know that winds influence water levels by up to a foot, especially in the summertime when you get the sea breeze, but could also be during winter storms. And we know that pumping for the California Water Project actually can decrease water levels by around a foot in the southeast corner of the delta. And so that's potentially an opportunity as well, at least in that area, or a risk if you don't pump as much water during a storm, let's say. So putting it all together, we can make predictions using various sea level rise scenarios of what might be the total rise between the year 2000 and 2100. And again, if you just take a look at these colors, it's very variable, right? So anywhere from 3 feet to 4, from 1 foot to 4 foot, 0.3 to 1.2 meters. That means that there's going to be some winners and losers potentially, especially when you start overlaying this with the built environment, with the levees, with where the assets are that you want to protect. So this is some preliminary analysis, just taking these long time series, augmented by putting some extremes from that are missing in, with a regression approach. You can actually see the time series. There's some places that are very variable, other places that are not as variable. But you also see a transition between coastal and riverine influence. So anywhere where the 10-year flood level is high, so like in the southeast and the northeast part of the delta, those are river-influenced areas. Anywhere with the blue is more of a coastal-influenced area. So what you need to worry about changes too as you go, depending on where you are. And then you sort of see that reflected in the levee heights. And I did this quick analysis to see at what point would the federal levee safety standard be triggered, and how many years from 2025 would that be? And pretty much in the riverine parts of the system, that's not an issue. And my hypothesis for that is that those levees were built to a system that doesn't exist anymore. So they were built in 1900 when there was hydraulic mining. The water levels have actually decreased since then. If you go to the more sort of coastally influenced part, there are places where the levees are low relative to the 10-year water level, and there's more susceptibility to breaking or to overtopping. And you can see that if you take a look, I'll just fast forward through this. What the black curve is, that's a high water curve during 2017. And the point clouds, those are the levee heights along the San Joaquin and the Sacramento River. And the blue coloring is places where there's significant subsidence in two successive LIDAR surveys. And the red is where there was an increase in the level, and that might be from, say, construction. And the take home is, if you look at the San Joaquin, if you look at the sort of coastally influenced part of the regime, the water levels are actually pretty close to the levee heights. There isn't that much freeboard. So yeah, I think the take home is that the history matters. It matters for where the susceptibility is. It also matters where you are on the river flow to coastal gradient. What we do in the watershed matters because that changes the amount of flow going into the system, but also how we manage the system. If we build a tunnel from Sacramento to the southwest corner of the delta, that's going to decrease water levels in one place and increase it in another. If we change the way water is routed through the delta, it's a lot of channels. That will also change water levels in one place versus the other. And if we dredge or don't dredge, or depending on what happens with the morphology, if the sediment transport changes, we will also subtly change the tides, we'll change the mean water levels. It's a very complex system. All right, so yeah, so from my perspective, at least historically, humans have had a much bigger impact on the delta than any climate change. And the point at which climate change actually becomes more important may still be somewhere into the future, right? And so that is a question for those people managing it. What problem are you managing for? If it's climate change, you might have one solution. If it's local subsidence, it might be a different solution. And so these are sort of hard questions also because the science doesn't always necessarily tell you everything. And we have sort of this compounding effect where both of these things are happening synchronously and making it perhaps worse. I think with old records that we can actually learn things or actually relearn things. If you have had a chance to take a look at this snippet from the 1950s, they talk about the reduction in flood risk that happened due to making the channel in Rio Vista much, much larger than it used to be. So people knew about these changes, we have forgotten them, but I think they give us clues as to how the system works, what it is sensitive to, and maybe also clues to some solutions. So yeah, so what are some of the other sort of things, and I'm not a policy person, so this may be totally outside my wheelhouse, but just looking at the ultra-local sea level rise projections, means that maybe one has to plan ultra locally as well. You can't just take a look at what's happening in San Francisco and assume that's going to work in the Delta. I also think we need to think more about timescales. We know it takes a really long time to build projects, 10, 20, 30 years. And if there is a problem in 20 years already, we are in fact already starting behind schedule. I think we need more measurements, as has been mentioned this morning, particularly vertical land motion, understanding that better. Both the deep subsidence and the shallow subsidence, I think there's still a lot to learn and a lot to monitor. And I think we need more education. That was also, how do we, as scientists, transmit this knowledge? I think education can play a role. And in that regard, it's always really surprising to me that there's no coastal engineering program in the whole state. We have SCRIPS, which is a great oceanography program. It's more blue water oceanography, maybe some waves. But I'm on a project with Caltrans. They have no single coastal engineer working for them, which is astonishing. And hopefully no one's from Caltrans. All right, thank you.
Thank you very much. And now we have Romain Mandley from Department of Water Resources.
All right, I'm going to try to go faster because of the time. So I'm Romain Mandley. I'm the Climate Action Coordinator for the department. I think, first of all, I wanted to give a little bit back about my background, because I think perspective is very important when we talk about climate change and we start to communicate to like local entities. And so just, focus on the baseball player. I'm from Europe, so I don't like baseball bats, so that, I could use that here. I was a land surveyor, and land surveying is all about precision and accuracy. And then when I came here, I decided to work on water, climate change for a large organization. And working on climate change, we're not trying to look for precision. We're trying to look for accuracy to reduce the uncertainty associated for future conditions. And then throughout my career, I worked on many, many projects, different size, different type, flood, droughts, and so on and so on. So I have this like multi-aspect associated with it, and I use the tools that climate change are fed into. And so I understand like the challenges associated with that. And so that perspective is really like building into like where we're heading a little bit with the department. Obviously, with my collaborators in the department, we have a climate change program, and you'll hear tomorrow Michelle Jefferson, who's going to talk about our climate action plan, which is a free phase and how we are advancing it. But today I'm just going to talk about one climate change analysis that we did. So in the department, we have used both top-down and bottom-up approach, which has been discussed this morning. And right now, we're really pivoting toward a bottom-up decision scaling approach, where we really try first to understand the system performance as it is today. Because I think a lot of people don't realize how the system works. We have this conception of how it works, but actually when you start to run the models, it may like induce to a different level of performance. And once like everybody is like agreeing on like this level of performance, then you can start to stress test the system to understand like when the system start to fail. And you can overlay that with the general circulation models to see how future adaptation strategies can perform under future conditions. So really looking at global warming level and when to trigger adaptation strategies. So we have definitely transitioned toward this direction with the department. In green are the top-down approach since 2006, so 20 years of expertise in that space. And then as recently, since like 2022, we really pivoted toward a decision scaling stress test approach while combining the general circulation models. So I'm going to go show you one project. I wish I could have a seminar about all the projects I've worked on, because I think they all have their own granularity and sophistication, but I'm going to focus on this one, the FEMA Cooperating Technical Partners Program Floodplain Mapping Pilot. So it was a pilot that we performed in the Chalmey watershed in the San Joaquin Valley, so not quite in the Delta, But there's also a pilot that actually inform right now the Central Valley Flood Protection Plan Update 2027. So what I'm showing here is actually being applied for the whole Central Valley. So the process is the following. We have our weather generator, and you can, if later on I can forward you like the link to the weather generator. And we feed this weather generator output into our hydrologic model. And the hydrologic model is creating multiple potential future conditions perturbed by change in annual precipitation, annual temperature, and we added the thermodynamic effect, the Celsius-Clapeyron, into it. And then that, we can evaluate many, many metrics. One key here is really to evaluate metrics who are natural metrics, who are not biased by anthropogenic impacts. And so going back to Mike Dettinger, obviously if there is a wildfire upstream, that surface response may change. But to which degree, I think that's something that can be very quickly done through sensitivity analysis. In parallel, we are using the LOCA2 CMIP6 data. So all the ensemble, like the 200 GCM plus all the SSPs plus variants of each of them. And then we are able to superpose this GCM based on change in precipitation and temperature on top of the surface response to provide a quasi probability of future conditions. And so that provides us a likelihood of future condition that an economic researcher can use to actually value the benefits of a project economically. So first, the weather generator real quick. So, we work on it with Scott Steinschneider at Cornell University, and we get Scripps Institute QAQCing it. So we feel really good about it. There is many ways that we can perturb historical data who has been detrended. We can change the temperature, the precipitation, the thermodynamic changes, so the Celsius-Clapeyron, you can modify it as you want. And then also the dynamic changes, something that was cursed about this morning when I asked a question. That's not something we are exploring right now, but we have definitely a time series to look into it. The weather generator can perturb historical data. That's what we have been using so far. But we can also create 1,000 years of data. We can look at very deep droughts from, based on stochastic information as well as very extreme precipitation. So we use the weather generator we feed this weather generator input into hydrologic models. For this specific effort, this 100-year sequence of data. And then we have 23 perturbations, and then we can develop unregulated flow frequency curve. And I'll zoom in a little bit on this curve. So here is an example of the 7-day, 100-year unregulated inflow into Don Pedro for current, with the 0-0 change, current conditions. And you get a change on the y-axis on the temperature change, and then x-axis on the average annual precipitation. Again, we have the thermodynamic effect into it. So for each change in 1 degree Celsius, you have a 7% per degree C in extreme, on the one hand, on precipitation, but also the drying off effect of the thermodynamic procedures. Currently, it's the current 100-year flood is around 50,000 CFS. That's unregulated, so we don't have a reservoir or levees or anything. It's really the maximum flow. And then we can superpose the GCM that we sample 10,000 times because we want to make sure we are comprehensive and that we don't miss a blank spot in our out of the GCM that has been produced by Scripps and others. So by 2040, we have an increase on flood flows to 65,000 CFS, and by 2070, increase of 90,000 CFS. And that's if I look at the central id of this cluster of data points. So now by superposing these two information, I can create cumulative distribution functions. That's an example by 2070. And I can say, well, I want to know what is the median conditions, and you can find the corresponding unregulated flows. And I mean that all the combination of temperature and precipitation through the surface response can correspond to that flow. Same thing for the 25 percentile, maybe a more conservative value, and same thing for the 5 percentile exceedance probability. So again, we may not need to use like the most extreme climate change projection to inform our probability. And some of these models may be way too warm or providing maybe like bias projection about the futures. And so it's really more probabilistically driven. Fast forward, we use this data to transform on-reg to regulated flows. And now you can see how that looked like for the city of Modesto in autonomy watershed. So that's current condition, 2007, that has been detrended. You see that the channel capacity, by the way, is like around 15,000 CFS. So if you recall, like my graphic, unregulated maximum flow without reservoirs, we were getting at 50,000 CFS for the 100-year flood. That's looking at 2040 for these 3 different levels of concern. Yellow, 50 percentile, orange, 25, and like the red, the 5 percentile, so the most extreme. And then by 2070, you can see that the yellow, orange, and red are pretty much superposed on one top of another. The reason behind that is that you need to think about the watershed on this construct and this topography. And so the increase in flood volume may be much larger, but like the change in stage may be very small. And so that you look at the very extreme event or like maybe more middle of the ground level, the change is very small. So you need to take that into consideration also when you do adaptation strategies. That's my last slide. One more pitch is that in relation to Firomar and Floodmar, next week on Tuesday, the department has a science symposium where we will talk about actually the San Joaquin watershed studies and show you like early results. So the approach, the climate change approach is used similarly to this study, and then we look at different level of Floodmar implementation. So on that note, thank you.
Thank you. And rounding out our panel is Liz Crossan from Metropolitan Water District of Southern California.
Thank you so much. Thanks for having me today. So get ready to kind of shift that really technical scientific mind to how we might translate some of those concepts into a planning document for a large and very political water agency in Southern California. So this has been a great conversation for me to be a part of. I'm the Chief Sustainability, Resilience, and Innovation Officer at MET. It's a new position. I've been there for a little, like 3.5 years. And then when I got there, I was charged with leading our climate action and climate adaptation planning processes. So that's really been my focus. So I really do see myself as an interpreter between our science and technical staff, our water resources planners, our science team. Sean Acuna is here from that team. And I'm the one that's kind of translating it, interpreting that for our board to help inform decision makings moving forward. So I want to talk a little bit about this planning process that we've engaged in, what we call our climate adaptation master planning process. So I'm sure a lot of you are familiar with MET. If you're not, we're the nation's largest wholesaler. We were started almost 100 years ago and really based the entire operation on importing water. So originally we built an aqueduct from the Colorado River. A couple decades later, we joined with the state to build the State Water Project. And for a long time, our agency really relied on those imported sources of water to facilitate the growth in Southern California. So we do provide water for 19 million people. That's about half the state through 26 member agencies. And I will say that in recent years, there's been much more of an interest in really looking to not only just conservation and efficiency, but also looking for new sources of water and local water supply and helping to invest to reduce our reliance on imported sources. And part of the biggest benefit of Metropolitan and coming together with these 26 member agencies is we can do this all together. And so I think, for academia, for the science community, when you think about kind of where you could have the biggest impact, an agency like Metropolitan Water District is pretty significant. We have these 26 member agencies in 6 different counties and cover a very large area. But that also allows us to really scale up whether that's particular infrastructure investments, research and studies, And so our policy statements, and so legislation, those are opportunities that I think Metropolitan really brings because of just our large scale influence and potential. So this is just, to demonstrate kind of where our water comes from. Again, the State Water Project, the Colorado River, we've been investing in local. The city of LA has its own aqueduct from the Owens Valley that also produces water, except in those really dry years, of course, which we're seeing more of. So the way that we kind of started this climate adaptation planning process is our water resources team has done a fantastic job for a long time planning for the fluctuation in hydrological cycles. So we know there's drought, we know there's wet times, and we really wanted to, we really have done a good job in planning to address that variability. But I think more recently, especially in the last 5-6 years, we've recognized that there are more extreme events that are happening and impacting our ability to deliver water. And there are also other impacts that aren't just drought related, hydrological related, that are compounded by those things, like many of you have talked about, whether that's wildfire. And I really related to the gentleman from Colorado when you think about the compounding impacts of really wet weather followed by dry weather, followed by and you got really wet weather with high vegetation growth, dry weather and winds, and that's what we saw in January of this year in Los Angeles County. And so really, and some of Metropolitan's infrastructure was immediately threatened by those fires. And it really is a wake-up call to all of us in thinking about how do we best protect our infrastructure and continue to deliver on our mission. So, that's just one example, wildfire. We also are heavily involved in the Colorado River and negotiations currently advancing there. And so we're seeing reduction in imported supplies from the Colorado, threats to our in-basin systems, as well as obviously in the Delta. And so this all kind of worked together to really be a catalyst for our board to look at how do we best adapt, how do we make decisions on these big investments that we know we need to make. And in particular, our board recognized that we do have some big decisions. We have a large-scale Delta conveyance project. We have Sites Reservoir up in the northern Delta. We have our own regional recycled water project called Pure Water that we're thinking of investing in. These are all billions of dollars, not to mention all the infrastructure upgrades we need for our aging infrastructure. And so our board really asked us to develop a decision-making tool that would help inform them. Nope, that's the wrong way. I'm going to skip this because you all have seen so many. It was pretty silly of me to think I should include a technical climate change runoff slide in this audience. So just to tell you a little bit about the plan, we really are incorporating, an adaptive management approach to everything we do, and really what we are attempting to do is integrate our water resources, our climate planning, and our financial planning. Our business model is to sell water. That's how we were created. That's how, that's our major revenue source. We are selling less water. We have invested in conservation and efficiency in Southern California. We're also seeing in times of drought that we need to do a lot more messaging on just that behavioral conservation as well. And we're becoming more efficient as a society. And so I think that when we think about our business model in a climate changed environment, we have to think about different financial tools to help incentivize adaptation, to help really find those ways to get multiple benefits from our investments, so that we can just be more efficient with our ratepayers' dollars. So a little bit about our master plan. It's not a bunch of binders on a shelf. It really is this adaptive management approach to planning. And so, we have committed to review and update the data that we rely on an annual basis. In the past, we've done integrated resources plans, and we'd updated on a 5-year cycle. We're doing regular updates on a 1-year cycle. Not that we're going to redo all of our modeling that frequently, but at least we're going to look and see whether or not any of the inputs have changed and there's new information that we need to be incorporating. And we're actually doing that right now. We're also considering a range of potential futures. So, in the past, a lot of water managers have always looked at, we think this is the trajectory that we're on for the future. Maybe we have like a buffer zone around that, but, we're looking at scenario planning. We're using scenario planning to be able to really look at a range of potential scenarios. And I'll talk about that a little bit more in a sec. And then the other thing that we've developed is a standardized way to assess these big decisions. So we have a set of criteria that we're applying to evaluate each and every project. We'll use that criteria to evaluate Delta conveyance. We'll use it to evaluate our pure water program, new conservation programs, new reservoirs. It also makes a lot of sense for us to use that tool to evaluate investments in the Delta that we may be interested in making. Many of you may not know that Metropolitan owns 4 islands in the Delta. We originally bought them, because we thought the conveyance would go through there. That's no longer the case. But we were making investments because we understand the importance of reducing subsidence, of restoring that habitat. We have, our science team is looking at all sorts of different projects related to fish recovery, as well as water quality. We have long-term agricultural leases that we're shifting from corn to rice to reduce subsidence, to sequester carbon. We're restoring wetlands. And so really trying to use those islands to think about how do we improve the through Delta conveyance that we know is having a major impact. In addition to it, I'll just mention this is a small piece, but I think it's a really good sign that Metropolitan, along with DWR and PG&E, have invested in some upper watersheds, some forest resilience projects up in the upper Feather River, to really think about how do we invest in fire resilience, fuels reduction, watershed restoration, because we do know, like many of you have actually, scientifically demonstrated, that there are major benefits downstream if we can restore those upstream ecosystems. These are the scenarios we're using. Just, they range from high and low demand to stable and unstable imports. The inputs in here are RCP 8.5 and 4.5. We also have demographic data that we put into it, and this is some of what we're updating now is related to population changes in Southern California, as well as how much storage we have, how much local supply is being produced. So that's what we use to then set targets. And in our climate adaptation plan, we've set some pretty large targets of like, what's the worst case, RCP 8.5 and those other contributors. What's the worst case? How much water do we think new water might we need in the future to reduce our shortages? And that's what we're striving towards for planning, not for implementation. And I think this is a really important thing for policymakers to understand is we may need to plan for those extreme scenarios, but that doesn't mean that we're gonna make those investments today. And what we could really use your help with is how to plan out on a time scale when we might need to make those decisions to make those investments. So when are we going to see the most extreme impacts? When do we need to be ready? Where do we need to be ready? Those are really important questions. This is just here to demonstrate that we have also made some policy commitments that I think you all can help us fulfill around ensuring that we're assessing climate risk in all of our operations, that we're incorporating the best available climate science and other information, and that we're not only committed to delivering acre feet of water at a cost-effective outcome, but we're actually really interested and committed to resilience long-term, to environmental co-benefits, and affordability and flexibility. So I know I'm running out of time, but I just wanted to quickly show you the 6 criteria that we're evaluating all our investments with. So again, we used to really just look at how much water and how much is it going to cost. This is a different approach for Metropolitan Water District. And this is a pretty diverse agency. It's Southern California, but we range all the way from Inland Empire and Riverside County to San Diego to Ventura to LA to Orange County. And we've all agreed that these are the 6 criteria that not just is reliability important, but we need to think about equity, environmental co-benefits like ecosystem function when we make decisions about investments. And then we're going to report on our progress in those signposts I mentioned as far as the inputs to our model on an annual basis. So I see why you all talk so fast, because once you get up here, you realize that you have to. All right, thank you.
Thank you, Liz. That was great fodder for our next conversation. So I think actually all the panelists, if you could join us in the front, so don't get too comfortable back here. And let me just quickly explain to everyone what's happening. We're gonna now have a time to connect the dots across these talks in this panel Q&A, and then we'll have a break, and then we'll continue the conversation drawing upon everything we heard today to develop some cross currents in terms of using the science and thinking about how it informs some key decisions. So let's see, I need my questions, just in case you don't have any. So yeah, if folks, I want to connect one dot that occurred to me. So Mike talked a lot about how we have these environmental restoration opportunities to mitigate effects high in the watershed. And I think Liz brings to the conversation the idea that there's also human behavioral mitigation. So that both there's environmental and human responses that we can control here. So just want to bring that up. So yeah, we're basically opening things up to questions now. If folks would like to grab a mic and ask a question, we can move ahead.
My name's Bruce Town, and I wanted to ask if Metropolitan has, in their feasibility studies, looking at desalination as another resource.
Yes, thank you for the question. We have two studies going on right now related to, one is ocean desalination and one is related to groundwater desalination. And we're following the State Water Board's ocean desal policy for the ocean one, and really just looking at projects that have a lot less environmental impact with slant drilling. Obviously, some of the other challenges are related to power use. But there's also, one of our member agencies, actually a few of our member agencies, and we've put in about $500,000 to this technology called, that's basically an open ocean type desal that really uses the pressure of the deep ocean in order to move it through the membranes and then pipe it to the sea or the shore. And so it's less energy because you can use kind of that natural pressure, but it also reduces the impact to marine organisms. So, again, we want to think about the environmental co-benefits and any unintended consequences from any new investments that we make.
Thank you.
Go ahead, Diane.
Well, thanks for these really interesting presentations. I'm from Colorado. We don't have earthquakes in Colorado, but you guys are here in California and we have earthquakes, and I'm interested in whether or not some of these issues involving the levees and the subsidence are exacerbated by, does it take a smaller earthquake to make a problem even bigger than in the future? Maybe I'm not saying this correctly, but people are nodding their heads.
Yeah, so I'm not a tectonics or earthquake person, but I have read that there's a pretty decent chance of an earthquake happening in the Delta in the next 20, 30, 50 years. And that is actually one of the mechanisms of possible failure for the levees. If there's a geotechnical engineer in the house, maybe they could speak to that a little bit more.
Just a slightly different perspective on that, not disagreeing at all, but is that one of the ways that some folks in the USGS and I were thinking about it was, you don't have to think about, we're going to have a flood and an earthquake at the same time. That can happen. It certainly can happen. What you have to worry about is if you have an earthquake big enough to damage or weaken the levees, you have roughly 18 months before at least some of those would be fixed. So you have the probabilities are earthquake, odds of an earthquake, and then within the next, call it year, 18 months, whatever number you want, there being a major flood. So it's not a total, crapshoot as to whether or not you can get the two lined up. They don't have to line up perfectly.
Romain, did you want to add to that?
It's working? Yes. So first of all, like the department is like putting, I believe, every 2 to 5 years a Delta hazard mitigation plan. So where we do tabletop exercise internally about, hey, if a earthquake happened, what would be our response, and how to deploy material and staff on the ground. Also, every time there is an earthquake, the department is patrolling the levees to ensure they are like intact. But as you know, historically, like levees have been built on like very soft ground, and so when we provide grants to local RDs, we make sure that like the projects are going to withstand some level of like hazard in that space. We also like in relation to earthquake and climate change. It's kind of like hard to merge these two topics, but I will say, for example, in relation to levees and their fragility, we are the first organization, actually, state agency, to put climate change requirements in our grant program in regards to levee investments. So it was through the Delta levee rehabilitation program. So there was like local entities who had to respond to like future conditions and how their project is going to be able to adapt over time if sea level rise was coming in. And that was the first in the state. So.
Can I just ask you to expand a bit on that? Because a key question we're trying to address with this panel is, do we have the science needed to support some of the management choices? So you just described using climate change in levee investments, but do you have what you need?
I think so. I think that was one of the questions of the panel. So it depends. Personally, I think we have enough data out there to do like informed decisions, as I share in my presentation. I think it really depends on like the risk aversion of people out there. So for example, like when we put the 100-year floodplain protection or like the 200-year level protection, that was not an economic decision. It was really like folks who came on the ground like say, that's a level of threshold we are willing to accept. And so if it's in that space, yes. However, there is some metrics we are missing. For example, especially in levee in the Delta, I'm concerned about wind, for example. If you have major increase in wind speed with increasing the waves and the angle that they hit the levees, there may be erosion over time. But if you look at what we did through the Central Valley Flood Protection Plan update and Delta Adapt, I think we have a lot of like answer out there, and I'm not sure if more granularity would help to get a better outcome or decision out there. So you come up to like in my mind more like process based on like how we use this climate change information in our system models, and also how we communicate climate change to like the audience for them to understand it, because that's very like I think in my mind like the difficulty.
Thank you. Yeah, Obey.
Thank you. Interesting presentations. So I'm going to try to connect the dots between many of you. I'm looking at long-term investment, and I think the Metropolitan Water District needs reliable water supply. And then I look, going upstream, I look at what we heard this morning. We're going to have a lot more interannual variability, whiplash, seasonal changes, and then multi-year droughts that Dan talked about. But I think Mike highlighted something important that we have also thought about. Many, modeling exercises don't look at the infrastructure needs including expansion of storage areas upstream. And I don't know how big is a site reservoir, but to me, that could be a problem in terms of assuring the water supply to downstream users. So my question is, and then coming back to the weather generator, that's an interesting approach. So my question is, do we know that we have enough science and tools to simulate either whether it's scenario planning or storylines to get some reliable reflection of these water supply scenarios into the future, accounting for all these expected changes that we heard about? Sorry, it maybe have been a kind of a long question, but
Okay, so in my perspective, it's really in the planning phase that you can explore the future conditions. It's not when you start to apply for a permit or design that you are able to look at, the whole range of potential future conditions. And so that was one of the key through our program and the climate action plan, which has 3 phases. Phase 1 is our greenhouse gas emission mitigation. Actually, that's number 1. That should be our investment, for everybody in general. Number 2 is our climate change analysis, and phase 3 is our adaptation strategy evaluation. So when I led the climate action plan phase 2, my goal was to really focus on our planning activities. That be the California Water Plan, the Central Valley Flood Protection Plan update, and then the Stewart Project Delivery Capability Report, because there are 3 major planning documents where we have the luxury to look at the whole range of uncertainty. And then based on this information, now you can zoom in about what are the best action to take. Now, you saw that we transitioned from a top-down versus bottom-up approach, and then we just released the Stewart Project Adaptation Strategy maybe a month ago, right? If you look at the different approach, the outcome is the same. I mean, that you look at in the Delta, and also the resulting effect of multiple adaptation strategies is also the same. The magnitude is slightly different, but the outcome in general is consistent.
Any other comments? Dan, do you look?
One little nagging issue that I don't think has really risen today is that there's paleoclimate evidence in California in the last 1,000 years of some really deep droughts. And this is one area where the GCMs, and I suppose weather generators, if you run them 1 billion times, might replicate something like this. But I don't think we still understand the dry episodes that Scott Stein uncovered in. Sorry, that's kind of scary when it's that close. I don't think we still don't understand those really deep medieval droughts, and that there's no doubt that they occurred. There's conifer trees that whose stumps are in deep water in Tenaya Lake and other river channels and so forth in the California region. And the lesson I think we draw from whiplash and variability is that, yeah, we get in these dry spells, but the atmosphere swings back in a few years, and we get a 2017 type of year. But those episodes were persistent enough that they allowed lodgepole pines to grow 60 or 70 rings. So how do we explain that? And that was in the Holocene period. It wasn't a fundamentally different climate state. We heard that there's some tendency for La Nina-like conditions perhaps to become a bit more prominent. So anyway, we might. I'm not connecting the dots to management. I think that's Romaine's territory, but it this is one signal that it's
it's a small odds, but it has enormous consequence.
I think another challenge that I see in this is, most water resources agencies, they do 20-year plans. And so the plan we're working on right now is 2045. And that's not even getting to, some of the first kind of extreme changes that we're predicting in climate change. So, and I was really struck by someone today talking about in the Sierras how we'll see, this shift after mid-century from forested environments to more shrubland environment, and how that's going to impact, everything that we're talking about when it comes to these long-term investments and the short-term investments we're making in that watershed. So I think there's a scale challenge between sort of what you're seeing in the academic community and what managers are using to make decisions.
Yeah, thanks. Stefan, while we're on, it's not quite paleo what you're looking at, but is there anything you've seen from developing the time series that gives you pause about how we're managing water?
Yeah, I mean, just looking at the 1862 event is really interesting. And I think in general, just looking at the historical events gives us insights into what's possible. And it's, like I remember 1983 and 1997, but younger people don't. So, so that's something that I always try to show them pictures and, be the grandpa that's telling the stories. But I mean, one other thing that I think you see is that we have a huge capacity to change our system. That's one of the lessons I get out of that. Like if you were to transport back 200 years, the hydrological system was completely different, at least in the Delta. And that means we have, if we run things right, it's an opportunity, but it's also like a warning in a way too. Just in terms of management, I think we often are compartmentalized in what we do, right? We just think about this project. There was a recent state law in California that all coastal communities have to have sea level rise plans, or were strongly suggested to have them, but it did not apply to the Delta, as if the water knows boundaries, right? And so that's something that I think just we still don't really have a good handle on, is how changing things in one place really affects the other. And that's kind of what we're talking about in terms of the watershed. But it's also true if you build a Delta tunnel. It's also true that there could be things that you do, dredging to the port of Oakland maybe has some effect in Grizzly Bay. And there's some, and maybe it's minor, right? Or maybe what you do in Napa matters. So anyway, thinking in terms of a system, and also thinking in terms of projections into the future, that there's also management scenarios. I don't think that's what climate scientists are doing at all, but we know it must be important, and that's what you see if you look back in time. You can see that, if you had just started in 1850 and kept the system as it was and did your climate projections, you'd be totally wrong.
Thanks, good perspective. Oh, Mike, go ahead.
Yeah, I'm going to raise another uncertainty, and that is, in order to do a lot of what we're talking about here, even the paleo stuff and the synthetic stuff and so on, you have to know which are the climate variations, which are the variables that matter. And that may seem really obvious, but if, a lot of times we assume that if we know the annual temperatures and the annual precipitation, that we're good to go. I mean, that's, and what we've heard today were things like the clustering of storms, I don't remember anyone actually saying it, but I will say it, can quadruple the size of the flood that you get if you start stacking the storms up too closely. And that's something that we're working, we've done work of late to try and trick some of the blue oaks in this state into telling us about the really big storms and maybe how often you see them from year to year and that sort of thing. But, unfortunately, we shouldn't be assuming that because it's something that we know how to generate or read out of the trees and lake varves or whatever, that's necessarily going to tell us what the real risks are.
All right, good points. And Anna's been waiting patiently. I did see the hands over here, but go ahead, Anna.
Thank you. And I think Liz and Mike, you actually queued up my question pretty well, and it builds on what Lisa and Obe were asking about as well. One of the things I'm most interested in understanding from this workshop is this transfer of knowledge or information from the types of talks we heard before lunch today to the work that you do and the work that we will hear about tomorrow, in terms of on what timescales does that happen? Does that transfer happen at all? Is the science actually looking at aspects of the system that are directly relevant to what you are doing? And so, this morning when I asked the question about what is the single thing that you feel we've learned most about in the last 5 or 10 years, I'll just really briefly read them off. So one was urgency of dealing with wildfires. One was the importance of the rarest events on overall outcomes. One was improvements in subseasonal forecasts of extreme events. One was time of emergence of low to no snow futures, recognizing flash droughts and connection to wildfire, and better understanding of where climate models are trustworthy and better understanding of local to regional responses. So keeping those in mind, and this is more for the management folks on this panel, are these advances in science being used in practice? If not, is it a timescale issue that it just hasn't permeated into your world? Is it that it's not directly relevant to your work? Is that there's a gap, or is there a gap in between where the science leaves off and where your work picks up? What are your thoughts on these high-level takeaways from this morning's panel in the context of your work?
Maybe I can take this question. I think there is many folks in the room I work with in academia. So the department is like making a strong effort to contribute, pay, and collaborate on like research papers. And Louis Conrad, who used to be with the Delta Association Council, is developing a whole inventory of like our contribution out there. And so the information, we were also the first agency to use the lookout to downscale in our decision making through the Seawater Project adaptation strategy and many others. So we're not waiting for the information. We are helping to develop the information in co-production with academia. The second thing I think what is like tricky is from planning to implementation of a project, there is some timeline associated with it, right? You may have a concept, but it may take between 10 to 20 years to actually make it on the ground, because you need the permit, you need the resources, you need the financing behind it to make it happen. And I think that's really like the predicament we are in, is that we have the solutions, but making like going faster is tricky, because we want to bring everybody on the same page, on the same time, and not leave somebody behind. And I think that's a difficulty. You look at Paradise Cut, for example, in San Joaquin Valley. It's a good project. It's an economic ecosystem value to like divert water from the San Joaquin Valley during large flood flows to like reduce flood risk in Manteca and so on. This study has been gone for like, I think the first CVFPP 2012. And right now we are in the middle of a feasibility study. And so that takes some time. So that's just an example. Same thing for like Firomar, sorry, Mike, Floodmar, Firomar. I think there is like, you'll see like if you attend the symposium, there is really multi-benefits opportunity to like capitalize on flood flows to do ground recharge. But like you need the collaboration and, bring people around the table and work together on it, and the resources associated with it. Otherwise, you will fail.
I'll just follow on that one, just say the FIRO work that's been mentioned. We began that, we pulled the first steering committee together around 12 years ago. And we finally got everyone to sign off on the plan. And this is practitioners mostly, but on the plan for the Russian River about 3 years ago, and we're still waiting. It's still on the verge of actually going into law. Isn't quite the right word, but it's as close to law as any of us care to get. And I don't think that that's an unreasonable amount of time, because I hesitate to say bringing everyone along, but having everyone at the table and everyone able to walk away at any moment. So you have to all work together to keep everyone at the table, and then actually getting to something that can be put into practice takes time. And if you're there for the short term, you might as well not be there.
Well, just to follow up on that, Mike, so I think we all understand what you're saying. Government processes work slow on purpose, because it does take time to elicit this information, right?
It wasn't just government.
Government,
It was
right,
the
right.
science took a long time. The engineering took even longer. The actual sort of having the engineers convince themselves, because there was nothing that scientists like me and others were going to do to actually convince them. They were brought along, they saw, hey, this might work, you're right. I didn't think it would work, but this could work. But they had to convince themselves. And then finally, you have to get to the place where you're writing regulations and actually changing the regulated rules that in the case of Mendocino, that the reservoir will be operated for until some other group of crazies come along and make a case for changing it later.
Okay, what I was getting at was, if you learn something in a decade, say it takes a decade, if you learn some novel piece of climate science, is the process able to adapt to that, or do you have to still use the science you started with,
Oh, no, we were continually updating. We were continually changing.
Okay.
It's essentially like all the environmental decisions where it's best available science, and that means best available now.
Okay, well, that's good, because then that's not really a lag in a sense. Yeah, Liz, go ahead.
I agree with that for planning purposes. I think that where I see the disconnect is in the implementation on the ground. I mean, we're a very large agency, 2,000 people, half of those people are in the field operating our system. And so getting climate adaptation considerations into the operational functions, into the asset management functions, it's that nitty gritty stuff that can take a long time to implement. It's a real change in approach. It's a paradigm shift for an agency that's almost 100 years old. So, I'm always interested in, new ways to think about how to kind of get the buy-in from the bottom up in order to implement these things with the urgency it demands.
Very interesting. Okay, I think we should take 2 more questions. I'm sorry, Ellen. So we have already one lined up back there, and then we'll go to this first table, and I think we'll take a break, and we'll have time for more questions in the next session. So.
Hi there, I'm Laura Feinstein with San Francisco Estuary Institute, and I'm interested in the idea of doing the headwater restoration in order to, do all the things that we need to do in the face of climate change, increase storage and slow runoff. And I'm curious to hear if people are doing research to really understand the scale of that opportunity. Like, to what extent could we increase storage, for example, in the headwaters? And if so, who's doing it? Or is this a big gap?
Specific things, the headwater restoration and that sort of thing. It's the, shall I say, it's the appropriate agencies and people, frankly. I'm not one of them, to be perfectly honest. It's the Forest Service, it's the Sierra Nevada Conservancy, the Tahoe Conservancy. You can kind of come, I believe the Bureau of Reclamation of all people might be in there in the mix. And then the various academic institutions that have something to offer are part of it. And so, I mean, the trick is, I was going to say, the trick is with FIRO, one of the tricks was we had people who were the actual guys who turn the big valves, which they don't actually do anymore, but turn the big valves to operate releases from the reservoirs at the table, our first one, plus their boss and their boss's boss, so that it wasn't just some guy saying, oh, that would be great, with their boss saying, forget it, can't do that. But so we, I would say, have the people who are actually going to end up have a representative of the people who are going to implement these things, whether it be forest restoration or something else, at the table from the start. This shouldn't be an academic exercise.
So we're part of a few pilot projects up in the Upper Feather River watershed, and as well as DWR. And it's a unique kind of financing approach where there's these forest resilience bonds that have been set up by an organization called Blue Forest. And so beneficiaries like Metropolitan, DWR are paying into this forest restoration project with all the same partners that Mike just mentioned, in order to actually collect data to demonstrate the water supply benefit that an investment like that could yield. And so, that's really us trying to, invest in something, but at the same time, try to demonstrate that there's like a way to quantify the benefits that our agency would get.
And just to add, Carrie from this morning, and I'm not necessarily seeing her. Oh, is she still there? I'm not seeing her. But anyway, she's a person who you can talk to about that sort of thing. She's more on the modeling side and the data, the data massage and that sort of side. But, it's people like her who are doing some of the speculative, imaginative stuff alongside the folks who can keep it real.
Okay, if we're not seeing any other looks from the panel, let's have our final question over here. And I also want to acknowledge that we do have some questions online. I'm going to, some of them are detailed and we'll respond in the chat. Some are big picture, and I'm going to hold those to the next session. So.
Yes, so I have a question for you, which is whenever DWR looks at a solution, how do you evaluate how long you have to implement that solution for it to be viable?
So you mean like the lifespan of the project?
Climate change is happening and changes are accelerating, and
So,
how long do you have before the solution you're implementing will no longer work?
It depends, right? So first of all, we need to respond to legislative requirements in relation to major planning activities, right? So the CVFPP has a 30-year planning horizon for investment decisions. We decided to go past 30 years for our climate change analysis to 50 years. The DCR has a 20-year planning. The State Water Project Delivery Cavity Report has a 20-year planning horizon. So we need to respond to these legislative requirements first. Now, moving forward, I think what we want to do, and you can look at the conclusion of the State Water Project adaptation strategy. We talk about global warming levels, where we want to try to make the linkage between our adaptations, when to trigger them based on global warming level, because that's really where the IPCC is heading. If you look at the language and what they are proposing as tracking and monitoring the information, that's what really they're pushing for, global warming level, which is increase in temperature over time. And so I can envision that as we progress in our climate change analysis and our understanding of how the projects are performing over time, that we will be able to look at global warming level to implement projects, or when to start to implement, or start to do the permitting. But also maybe if we see that there is a signal which is taking us to the wrong directions, that, oh, maybe that's a different adaptation pathways that we need to take. So we're starting to build this piece, but the challenge is that most of the most interesting solutions are multi-benefits solutions. So you need to look at it not only from a water supply standpoint, but also from flood perspective as well as ecosystem perspective. And I think that's one of the challenge that we already solved through our San Joaquin watershed studies, because now we have a uniform way to look at climate change. So it would be trivial in my mind to be able to like start to evaluate when a potential solution is not viable anymore, right? But right now also, we need to be realistic that like our projections are up to 2100. There is really nothing outside this envelope we can tell us what's gonna happen. I mean, it would be ludicrous for me to tell you exactly where we're going to find ourselves past 2100. So we need also to be realistic on that planning horizon aspect.
Do you do this with modeling, where you model how long you have?
I mean, yeah, like for the San Joaquin watershed studies, we're evaluating flood-mar, FIRO-mar, right? And so we can show, and we're gonna have a dashboard, we can show like, you know, how far FIRO-mar is providing the level of benefit that we're expecting until climate change is like picking it up, and then we have another challenge at hand. The idea is really to try to find like solutions who are, you know, that you can build on top of, right? To make them flexible enough to address this change. Think about a levee, right? So we may have a specific footprint for a levee size based on like 2070 projections. So you may want to set, like, think ahead and buy the easement to create the levee footprint a bit larger to like increase its size. You know, but again, 2070 is like very far, but at the same time, very close to us, right? It depends on how you look at it. And it's hard to predict what's gonna happen past 2070, 75. I mean, at least in that space, I don't know, Dan, if you have a response, but I would, you know, my betting on like what exactly is gonna happen with a ENSO, PSO change and like change on like, you know, the movement of like the currents, you know, how they're going to change, that's still like a big gap.
Let me take you to the opposite end, which is that, you know, in the future, we're going to have sea level rise, and that's going to bring more salinity into the delta, and depending upon the water level in the delta, the salinity line may change. You will have a certain amount of time to implement a solution in order to deal with that change in salinity, which might be temporary, right? Or certainly will be variable. How do you model that? Do you model that so that you know how long you have?
Yeah, we have, you know, we use a schism model. We have very sophisticated models in the Delta where we can look at future condition. I'm not sure about this specific question because I'm not part of the Stillwater Project division. I'm with the Division of Planning and everything else but Stillwater Project, but I'm certain my colleagues look into that already.
And maybe we can follow up on that. Oh yeah, go ahead, Stefan. Yeah.
Yeah, the saltwater intrusion is interesting because it does sort of illustrate a couple different management approaches. When river flow gets really, really low, the state now has the ability to create a temporary dam across the Falls River. It's one of the channels. And that allows them to reduce the flow from 4,000 to 3,000 CFS at the same time protecting the water supply. And they did this on an emergency basis in 2015. And then they went and they got permission to do it once or twice a decade going forward. And what I find really interesting is when there's an emergency, all the usual environmental laws get skipped and they can just do something really quickly. But then we know we have this long emergency with climate change and it's kind of slowly accelerating. And we have this sort of non-stationary system that the climate scientists can see coming. And everybody here had some version of that warning, and yet the system, the political and environment, you know, legal system that we have is just sort of, you know, is very, very slow compared to the problem at hand, unless there's an emergency. And I think Dan mentioned that earlier today, that if there's an emergency, then people start to think about solutions. That's what happened in Hurricane Katrina as well. Scientists had warned forever that subsidence was a problem there, that they were due for a hurricane. And arguably, not enough people listened. And I don't know where the disconnect is, but and I personally don't know how to take my results and actually make them into policy, but.
Well, these are good thoughts to end on, Stefan. Thank you. So I think you're touching on this idea of dynamic adaptive planning that some of us are talking about in other parts of the ISB. So hopefully we can marry all these ideas together. Let's give a hand for our panel. So now we have a short break. Oh. And when should we? I know we're behind schedule, so how long was the break supposed to be? We have a 20-minute break, and then please come back. We're going to have anyone else in the audience who has something to add to this conversation about research they're working on is welcome to stand up and talk a little bit about that, and then we'll open it up to broad questions like how to implement adaptive management. Thanks. All right, welcome back, folks. I think we're going to have some more interesting information coming our way, as if you haven't learned enough today. We have an opportunity now for those in the audience who were not given the opportunity to present, but who might have something to contribute in terms of how their research is forwarding the use of climate change in adaptation and decision-making. And so we're just going to open the floor up and see if anyone wants to talk about that, and then after that, we will just basically open up into questions for a while, and then we'll have just a quick wrap-up where we'll ask folks to respond to a couple poll questions and give some summary thoughts of the day. I'll start us off on that, and we'll add. You can add. So yeah, I think with that, I'm gonna some people were aware this was going to happen and may have prepared some things, and others of you can feel free to be free form. But who would like to share some work that they're doing on climate change that they think advances this conversation? Maybe everyone left has already presented. Do we have any volunteers? Oh, I see Maggie Chrisman has volunteered.
I'm somewhere in between being prepared and being off the cuff. Yeah, no, I appreciate the time, and I like this kind of way to end the day. The thing I'll share about is something you heard a little bit about earlier today. It's called the State of Bay Delta Science. So a couple of the authors of chapters presented, and there's a conceptual model that was developed for one of the chapters up on the wall on the left over here, or my left over here. But essentially, the State of Bay Delta Science is a synthesis and communication effort that the Delta Science program coordinates. It's moving into a model where we're releasing updates every 2 years. And so the current update is a themed edition that explores extreme events and impacts of these extreme weather and climate events on the Bay Delta. And so there's separate peer-reviewed publications that just got released in San Francisco Estuary and Watershed Science. In the September issue, we had a chapter on wildfires, atmospheric rivers, and flooding, and a chapter on perspectives for future science. And then back in March, the first set of articles were released, and they explored heat waves, rising temperatures, droughts, and governance. Definitely encourage you to check those out. It had a very similar theme to what we were talking about or what we were hearing about today. Looking back, SBDS kind of focuses on the last 10 years or tries to emphasize the last 10 years of research. Because we hadn't explored this topic before, we took a little bit broader look at it. But there's lots of great takeaways. Each chapter highlights where we are and where we think we should be heading and highlights important knowledge gaps. And then the last chapter, I think, is really relevant for tomorrow's breakout group, so I'll put up a little plug-in for the perspectives chapter. It has 5 perspectives that the editorial board put together to kind of highlight where we think we should be going. And a lot of them are about leveraging what we already have in the system and just looking to the future to kind of take advantage of those and make the progress we need to meet the challenges we have ahead. And I should plug that Denise Columbano wrote that chapter. She led it for the editorial board, and she would be here, except she's in Hawaii right now, so that's why I'm talking instead of her. But I want to say that she did a great job with that and with coordinating the whole thing, so just wanted to throw that out there. But happy to talk more, but hopefully that's the right level.
Yeah, that was helpful, Maggie. Thank you so much.
Yeah, I just want to comment on that, and we reviewed many of those papers. Thank you for making those available to us. I think we prepared a summary actually, and they were great papers, and I think they're very valuable information in those series of papers. Thank you.
You can hang on to that. Okay, and other science or any really burning question or comments that anyone wants to make.
So I'm channeling Dr. Nyman here in asking about what about these beavers that used to be so abundant 300, 400 years ago, and then they were trapped out, and we're talking about using the past to understand what can be done in the future. Has anybody done any modeling in terms of the watershed retention and mitigation of floods, where the scenario is the abundance of beavers 300 or 400 years ago? Because we know that that was possible.
Do we have any beaver experts in the room? Mike?
I'm not a beaver expert. Truly not. But, the real thing I don't know is whether it's been done with modeling. But certainly there's been a lot of work in Colorado, in your home turf, on this sort of thing, and as well as in the high areas of the plains. But I don't know about modeling, sorry.
Thank you. Lauren?
Two old ladies hobble for each other. Without my cane. So I'm Lauren Hastings, formerly with the Delta Science Program. I am not a beaver expert, but I just happen to be aware that CDFW, so the California Department of Fish and Wildlife, has recognized the importance of beavers and now has a whole program on beavers and beaver restoration. It's the CDFW Beaver Restoration Program. I'm reading from my phone. I looked it up really fast. So public scoping meetings on development of a beaver management and restoration plan, July 22nd, 2025. So just recently, this is turning into a really big deal for, yeah.
All right, folks are commenting how easy it is to restore beavers. I also just remembered that I said I would forward one of the questions from the online guests to this panel. And what I remember is Deirdre Desjardins asked, how would we recognize nonlinear shifts in hydroclimate? And I know we heard a lot of presentations about that, but I think I'll add to that question, which is, is there something we can predict that would be useful for management and planning? And I know we've asked a lot of our panelists already, but if anybody wants to comment on that, I'm sure that would be appreciated.
Hi, Deidre. Well, that's a great question. The precipitation part of that water cycle chain is difficult because the spectrum is so white that it's hard to. There's a recent paper that Park Williams led along with other colleagues that was looking for essentially the change in extremes that models predict in various ways. Fewer wet events, more strong, occasional, rare, high precip events, and looked across the whole West and really was unable to detect that signal. I think we have to look at other parts of the water cycle than precipitation that are more integrative, that may be a low pass in order to discern various signals, whether they be nonlinear or whether they be linear. I think they're both really important. But I think this all gets to the importance of both modeling and an effort to collect climate quality observations, in longitudinal fashion. So I know that's not an acceptable answer, but that's my answer.
I'm just going to add that my main suggestion is that don't be fooled by 20 or 30-year change in the precipitation in California, because it can do that without breaking a sweat, and then still swing back. So just unfortunately, it's going to take some real serious time to get that one.
Can I related to that question? I think this morning either Daniel or somebody mentioned possibility of step changes. And we typically look at a linear trend in many graphics we have seen. And I've seen this in sea level, but in Florida and elsewhere, in around 2010, 2012 also, we almost see like a step change. So we need to understand, are there step changes and what are the causes of those? So the nonlinear variation could include. The big question is, are those episodic changes? Are those persistent? That cannot be answered yet, I think. Probably not long enough record to understand whether it will go back or not.
Yeah, if I may be so bold as to try to summarize what I heard today, I think I heard, we're doing pretty well to predict mid-century, but there's a lot of uncertainty when it comes to end of century. And so, yeah, we may never be good at predicting that. So that's the purpose of these adaptive management pathways. So yeah, thanks for that question. So I think the energy in the room may be waning. So I think, why don't we switch to the Mentimeters, unless there are other, oh wait, we have one more. Well, we do have some burning comments. Oh, look at you. Okay, good. I misread the room.
Hi, I'm Sean Acuna, Metropolitan Water District. I had a question when I was reading through that AI summary, which was interesting to read. And then the talks today talking about how well are modeling being integrated into decision-making, and then the fact that models are having a difficult time predicting in the future. We need better data and better models. I was wondering, I've done some work in decision science. I was wondering, why do you need to reduce the uncertainty in these models if the decision is already known? If you already know what your decision is, why do you need to reduce the uncertainty? I'm assuming the decision has a variety of ranges, so obviously you need to reduce that uncertainty. That's what I was thinking about, but I was wondering what you guys thought about that. If you know you need to plan for those things, like that paper that said in 2022, needs to invest in more storage, more resiliency, and more actions to help combat climate change. If that's already known, why do you need to reduce uncertainty? Why not just integrate what you have now and make the decision based on that uncertainty? How does that change your decision?
Me? Oh, wow. Yeah, wow, okay, I got really put on the hot mic after coming in. Good question. I guess what makes you confident that you've made the right decision if you don't have projections that also point in that same direction with the same certainty?
I'm not talking about myself. You guys already said you're doing certain things, A, B, and C, so you're doing them. But then you also said, I need better models, but you're already doing it. So why do you need the better model if you already know your decision? That's what I was just, maybe you don't know your decision. It just seemed like you did.
I was thinking you could pivot to what you were saying, that we know enough to do certain things. But
I guess I'll jump in. I think just because you need more capacity doesn't mean you know how much new capacity you need. So that would be an area where reducing uncertainties in models would be helpful. Or perhaps in an adaptive management framework, you might have made a decision, but having a better model might make you change your decision. I think it's this, to me, it's the contrast between you need to have a plan in place, but as the science improves, that plan itself should be able to change and adapt as the science improves. If you want to, hard code your decision, then I agree. There's no point in having a model at all. You could have done that with zero knowledge, right? But that's not necessarily the most effective way to support a resilient system. So I'm not sure I fully understand your question, but
No,
hopefully none of
that's
these
fair.
decisions are so rigid as to preclude the use of improved information.
Okay. It just seemed like, the only reason why I asked that, because it seemed like a lot of people in this room kind of already knew what they needed to do. So improving the model wouldn't have changed their decision. But what you're saying is it does, there's some perturbation in that decision-making where there's enough adjustment that you do need a reduction in model uncertainty in order to help you with the scale of your action.
Or to understand the risks associated with the decision you made. So for example, is a decision you made likely to, has a 90% chance of being effective under a future climate context, or does it only have a 50% chance of being effective under a future context?
Okay, that's very interesting. My experience with reducing uncertainty in some of our models, we found that it didn't matter. The decision was made. This is not a climate change decision. We're talking about a different type of water management. It didn't matter. What actually mattered were the decision makers' values. It didn't actually matter at all the information, which was very enlightening for us. And as a scientist researching that, I felt like I was redundant because it was a value-based system and my job was to find out more information. That I can grind that stone as much as I could, I would not change the decision.
Actually, I think I have a specific question, not to put Liz on the spot, but I was really, you had a really nice slide of something that I've been yearning for a while, which is I'm a big proponent of saying qualitatively adaptation pathways with global warming levels might be the best approach for deciding when to prioritize things and how to prioritize things and at what warming level do you start to initiate it. And it seemed like you had some really concrete numbers on the 1,000 acre feet of a certain project that you would then initiate at 2040 or something like that. And it was just, I don't know how much you can talk to it, but just what led to your certainty about that 1,000 acre feet value by a certain time window? Like what led to that confidence in that decision? And did the science lead, or was it value-based things, or both? Or I just wanted to know a little bit more the behind the scenes story.
Yeah, so those targets are based on the modeling that our team has done based on those 4 climate scenarios, including demand information as well and some other factors. So we've set targets to identify projects that will help us reach that volume, but the decision makers are going to apply their values and their biases in some cases when they actually make decisions on what they think, where we think we need to make those investments. So in no way are we saying that we need to implement everything, that in the worst case scenario at this point, but we want to be ready. And I think I do think our agency is starting to think in terms of staging. How do we stage certain things so that we can make decisions down the road? And that obviously lends to projects that are more modular in their construction than others. And so I think that's something that we're talking about a lot right now.
Yeah, I'll just be quick. So I'm Lisa Marie Wyndham-Myers. I'm currently the Delta lead scientist for the Delta Stewardship Council. And I wanted to highlight, so thank you for bringing that up, Sean. It made me think of the structured decision-making roundtables that so many of us have been involved with. And it really depends on who's in the room and what values are being talked about at the table before decisions can be made. One thing I wanted to highlight is that this is climate risk that we are assessing here. There's many risks, as Diane brought up, obviously subsidence, but seismic risk. And then there's economic risk and many others. So I think one thing I didn't hear yet that I'm really looking forward to hearing is how do we put climate risk in the framework of the overall risk assessment of choices that we're going to be making moving forward across the state, but obviously particularly in the Delta.
I can go. I didn't know if anyone wanted to respond to that. Okay, great. I'm Rachel Wigginton with the Delta Conservancy. My comments are a little bit online with Maggie's, sort of highlighting some of the work that we have been funding and helping to coordinate that I think is related to several of the talks that happened today, specifically thinking about some on-the-ground measurements and how those circle back up into the climate models that we've been discussing. So in 2023, 2024, we had our Delta Drought Response Pilot Program, where we were using remotely sensed data from the OpenET program to estimate changes in evapotranspiration on farm fields, where we had incentivized farmers to try to do some water saving practices, and we were able to use these climate models to then measure that. And basically what we found was that to have a big impact, we might need to hugely upscale the program and also really target higher elevation areas in the Delta. But as a part of that funding package, we've also funded Dr. Kosina Savankarev from UC Davis to do some micrometeorological measurements on some of these fields that are implementing these water saving practices. And she is working with the OpenET staff to try to integrate those ground truth measurements into that remotely sensed model. And that model was really trained on lushly irrigated areas, and we were trying to use it on these areas where we'd say, okay, don't irrigate, don't grow a crop, and trying to understand how well those model predictions were actually working at the field scale. So I wanted to highlight that. And then also I think sort of related to what Lisa Marie was just saying about the other risks, we at the Conservancy have been doing a lot of work on subsidence and potentially a protocol for the voluntary carbon market, which has been in place for several years, but is currently under its 10-year review. So that's a lot of the updated climate science going into those implementation approaches. And then I don't know if it's gauche to talk about a different symposium at this symposium, but in December, the Delta Interagency Invasive Species Coordination Team is having their biennial symposium, and that's going to focus on forecasting and modeling for invasive species in the Delta. So we're recruiting talks that have a lot to do with some of the models that we've been talking about today and how those changes in the Delta will also impact invasive species range and impact within the system.
Well, thank you for sharing that.
Yeah, so I wanted also to get another crack at the question of what are people in the audience doing that others here might be interested in. So I'm Laura Feinstein. I'm with San Francisco Estuary Institute. We work a lot on that downstream area that we haven't mentioned much, the Bay. But we also are active in the Delta and the upper watershed as well. We look at the whole watershed. And so some of the things that we're working on, we keep very busy. So I'm going to try to just highlight a few things. I think some of the most interesting work we're doing is some of the work that we're doing in the Bay that I think might be of interest, could be transferable up to the Delta. Some of the things there where I think we're making some really interesting progress is that we've got the Wetland Regional Monitoring Program up and running, which is collecting regular long-term data on wetlands throughout the Bay, including Sassoon. And I think what we're really putting to test is this idea that we heard some speakers talk about, which is that if you're doing really regular, frequent monitoring, does that allow you to accelerate the pace of your response to climate change? And that is really one of the big underlying motivations of the Wetland Regional Monitoring Program. I think we're also getting better at putting tools into the hands of people who need to make the decisions on the ground. So sort of trying to step away from issuing the reports that kind of give the instructions or the guidance, and more developing the tools and training people on how to use them so they can reach their own decisions. And I think one of the big lessons that we've learned is that it's often better to build a tool that is simpler, that lots of people will use and accept some uncertainty in it, than to build one that is more sophisticated, will give more certainty and more detail in its output, but which ends up being used very little or really needs a trained scientist to run it. And most of the agencies that you're hoping will run it, they might not have a trained scientist or not one that's trained in that particular field, right? So we have really been leaning into developing a lot of online tools for understanding resilience and opportunities to build resilience in the Bay that I think could be of interest to people in the Delta. We'll be coming out with the State of the Estuary report. This is a regular report that San Francisco Estuary Partnership with SFEI puts out. It looks at the state of the Bay and the Delta. Lisa Marie, and I don't know if she's still here, but Martina were part of the advisory committees for it. And, you know, a little advanced preview, it's not really a very good report card. And we are at this point only seeing the very beginnings of the impacts of climate change on the system. And so I think that's something very important to hold on to, is that the Delta in particular is already in deep trouble as an ecosystem. So we are really starting from a pretty bad hole, and all of these changes that we're talking about are exacerbating it. And that is not necessarily a very hopeful thing to say, but I do think it kind of points to this idea that we do have enough certainty to know the sort of general direction that we need to go. We don't necessarily know precisely what should be the priority or the scale in every way, but we know enough to know a lot of the things that we need to do. Really quick, we are just about to start a project with 2 tribes funded by the Delta Stewardship Council, thank you very much, to look at traditional ecological knowledge in the management of Delta Tule wetlands. That will be out in a few years, so we should better understand how Indigenous people actively managed wetlands for the types of benefits we all want. And then last but not least, I wanted to talk about work we're not doing. So San Francisco Estuary Institute was very generously supported by the Delta Stewardship Council to do a really sophisticated tool that does require a fair amount of knowledge to run in GIS. It's called the Landscape Scenario Planning Tool. And it allows people to look at large-scale restorations across the landscape scale and quantify the benefits in 16 different areas, including a lot of the things that we've been talking about in terms of impacts on water quality, on biodiversity, on carbon storage, et cetera. And it's not being used. It hasn't been used once, quite frankly. And I think that that is, you know, we've talked about that disconnect between science and practice, and I think it happens at so many levels. And one of those levels, I think, is investing in that step that goes from we made the really amazing tool or we published the really great paper, and the getting out there and training people and what it means and how to use it. So I think that's just something for people to think about, is how much great work have we already done that we're not using? I think that's something we're thinking about.
I'm personally afraid to ask that question, but yes, thanks. Thank you for sharing that. Okay, well, any other science inputs? Oh, we got one more from Shoko.
Can hear me? Hello. Okay, Shoko Shimbrat, Delta Stewardship Council. Listening to you talk about, like, you know, how are we getting things out there? I'm also thinking about how we flip the script about not just like getting our science out there, but also how are we developing it with the user in mind. So it's like user experience. This is not something that is new, like all sorts of gaming this is a thing that is known, but like how do we prophylactically develop something before we create something that is just like not used? So I think that there are many different types of products, and maybe not everything is meant for everyone. Like there is science for scientists, but if you're thinking about management or other, you know, like how do you start at the beginning with, say, tribes like you're already doing, or members of the public? So just adding on to your point.
Thank you, Shoko. Okay, well, I think, given that we're close to when we said we would end, I think we'll skip a lot of the other stuff we were talking about. And I just want to thank everyone for hanging in. We certainly learned a lot today. I was thinking of recapping, but I think at this point, we'll wait until tomorrow. Anna will recap what we learned today, but I know I'm going home with a lot in my head to think about. And please come back tomorrow morning. We'll revisit those Mentimeter questions, which will include, have you looked at the conceptual models, and what do you think of those? And then we'll also be asking about what you learned. So if everyone can come back tomorrow prepared to answer those questions, we would love your thoughts. All right, thank you very much.